Greetings. My name is Manish Gupta, and I'm the founder and CEO of Shift Left. We are a next generation application security company. And so this topic is very near and dear to my heart, overcoming the challenges that we face in order to insert security into every pull request. In this presentation, I'll talk about why this is important to do and why is it challenging to do today, and what is it that we need to look for in order to make sure that we are indeed able to insert security into the pull request. So one of the things that has happened, over the last several years, um, especially with the rapid adoption of cloud, and is that each of us, each of our companies, we are developing more and more software in the form of applications that are serving functionality to our end customers, or in some cases internally to our employees. And as we migrate these applications into the hybrid cloud, the onus falls much more on us as individual companies to protect our applications, right? The attack surface is clearly shifting to the applications. It's not like in the past, hackers were going after the infrastructure, or they were going after the operating systems. More so, they were going after applications. It's just that in the past, we had an opportunity. Our architectures were such that we invested a lot in protecting the infrastructure and the applications. Cloud adoption allows us to free up some of that spend and focus on what's truly important, which at the end of the day are applications. Here are just a few examples to illustrate what can go wrong if we do not protect our applications properly. And the proper protection of applications has two fronts to it. One, how do we make sure that we can minimize vulnerabilities and deploy applications that are as clean as possible and as high a security standard as possible. And the second, which is, how do we protect applications in production? Because almost no organization that I'm aware of fixes all the vulnerabilities that they find. And when we look at the kinds of attacks that have exploited applications in the recent past, it's a bit of a surprise that it's the same age-old attacks that we've been seeing for about 20 years. In case of Equifax, a vulnerability in a library that had already been patched, or SQL injection attacks, they still are very prevalent. And on the right side are business logic flaws, and these have really come to the fore as we've started to adopt this new cloud environment, because it is new, because it requires some unique functionality, such as credentials and secrets in order for the application code to authenticate itself. People who are not used to such practices, developers can make mistakes and hard-code these credentials or leak such keys inappropriately to the wrong places, which can have significant impact to the organization. So these are the kinds of things that we are trying to protect by shifting security left, by inserting security at the pull request. Now, why is it important to do this at the pull request, one may ask. And before we answer that question, it is important to look at the modern CI/CD, or continuous integration, continuous deployment pipeline. Everyone is rapidly adopting DevOps, and COVID-19 has actually accelerated this timeline for most organizations by 3 to 5 years. I mean, the last 3 months in this crisis, one of the things that we have clearly seen is organizations that are agile, organizations that are cloud friendly, have done well compared to their peers. An obvious example is e-commerce versus offline commerce, right, or retail stores. And so large retail companies that have good e-commerce presence have navigated this crisis better than companies that didn't. And so the why are we doing DevOps? Well, that's not necessarily the focus of this presentation, so I'll skim uh, through it to essentially say DevOps allows us to both collaborate. It creates a culture of collaboration that enables agility, that allows us to develop faster functionality, or excuse me, that allows us to develop functionality faster so that we can deliver new functionality, new capabilities to our customers on a rapid basis. In a hyper competitive world, time to market can mean the difference between life and death for a company. And so, as we look at this CI/CD pipeline, some of this, of course, is rather apparent to you, but just to sort of walk through it so that we understand what some of the things that we are trying to highlight here is on the very left, you have many developers, and the key innovation of Git is to allow many of these developers to work simultaneously, meaning each developer has the ability to take a copy of the main branch into her feature branch and make changes. And whenever she's done, merge these changes into the main branch asynchronously. And it is Git that takes these changes that are coming in ad hoc and tries to figure out, well, Manish just made this change, and this is a change that Tom made, and how do I merge them into the new application? And the CI/CD makes this highly automated so that as developers are writing code within their own feature branch, as soon as they write it, the compiler takes over. The CI, continuous integration tool such as Circle, takes over, compiles the code, and literally provides immediate feedback to the developer as to whether this was successfully compiled or not. Right? All of this happens in a matter of minutes. And then from there on, the code is merged with other changes, built, deployed, tested, and finally released in production. Now, in this pipeline, when we take a look at where does security get inserted, well, it's rather late. Many organizations, it happens in sort of the test environment. And yes, in some organizations where they've already seen the need to move security left, you are probably doing security maybe at the build stage, right, instead of just test. Or maybe even further left, you are probably doing it at the commit stage, right? Which is good, but still leaving a lot of things left undone. And we'll talk more about that today. Now, when I say security here, I mean static code analysis, because it is clear that is the first and foremost technology, is the most comprehensive way to look at vulnerabilities in a piece of source code. So we run this. Now, typically what happens is there's the application security team right here that runs the tool that of choice for static code analysis. They find a bunch of vulnerabilities. And typically, just given the nature of these legacy tools, which are about 15 to 20 years old, they create a lot of false positives. And for all the right reasons, application security does not want to take all of these results with the false positives to developers, because after all, they're going to get laughed at. And so they spend some time triaging them, triaging the output of these tools, finding out the true vulnerabilities that should be fixed, and finally taking it to the developers.
Inserting security at this late stage in the CI/CD pipeline has significant challenges. As you can see, if you are testing the build here, this build has included multiple feature commits that have happened much earlier in the CI pipeline. And so as a result, the application security team no longer has visibility as to which developer made this change that might have caused this vulnerability. Even when you take this back to the developers, perhaps these developers made these changes that you're just analyzing 3 days ago, which is not a long time. I mean, some customers might have, days, perhaps weeks between the time the change was made to the time the code analysis is done. But as you can now also see that if you're taking back issue to a developer that made that change 3-4 days ago, you're asking him or her, for that matter, to think about what they were doing 3 days ago when they made this change. And so you're causing productivity impact. There's no reason, there's a good reason why developers don't really like to do application security. It's just additional work for them. It impacts their productivity. It doesn't allow them to be as productive in making changes that they otherwise would have been. Now, worse, given these legacy tools and the way the static code analysis is done, it usually causes false positives. And now these developers are not only having to not only having to deal with issues such as delayed reaction from the code analysis tool, but also with false positives. So now they're starting to spend time on activities that they shouldn't be spending time on. And how do they tell the tool as to how it could do a better job next time? Now, furthermore, if one developer's change was a foundational change for the second developer, whose change was a foundational change for the third developer, by the time this code is being analyzed and we've gone back to the first developer in this value proposition, any change that this first developer makes now has impact on the changes made by developer 2 and developer 3, further causing an impact to the developer productivity. So how can we get better at this? How can we make sure we can uplift the quality of security yet not impact developer productivity? Well, Git already has given us a model, right? I mean, that is the automation that the CI pipeline brings, where developers write code and as soon as they commit it, it gets compiled. Well, in the same manner, we should be running code analysis. Developer makes a change in her feature branch. As soon as the change is made, the code is compiled, and in parallel, we should be doing code analysis. So that for the first time ever, we are providing developer the information on vulnerabilities at the same time as we are providing information on bugs. Now, because this is being done for each incremental feature push, there is, of course, no longer any doubt as to which change, forget about the developer, but which change caused this vulnerability to take place. And this is still very fresh in the developer's mind, right? In fact, the rule of thumb you should be following is the developer made a feature push, and by the time she goes up, gets a cup of coffee and comes back, the code is compiled, and she gets feedback on the vulnerabilities, if any, that her change caused. But at the same time, developers are not security experts, nor should they be expected to be security experts. That is the domain of the security team. So, and security team, because they have a broader purview of the entire organization, they understand the importance of some applications that are perhaps customer facing, dealing with sensitive data, perhaps have more regulatory and compliance requirements. So that is what we should be able to do, is to take the knowledge of the security team and translate that into code, translate that into requirements so that we can automate that in the CI pipeline. So very much like we've automated we've automated DevOps by translating infrastructure into code. Very similarly now, we are starting to automate application security by translating application security requirements into code. Now, just because we do code analysis farthest to the left does not mean that the security team can or should not be able to do another scan later on in the pipeline. There are requirements in many organizations to have a report, have ample documentation on the vulnerabilities that existed in the application that was released in production. So this is not either or, but it should be and. Now, if you were to design such a system by using a code analysis product, the obvious question that comes up is, well, what capabilities should this next-gen static analysis product have? Well, clearly, number one, it needs to be fast. Why does it need to be fast is clear, as we looked at the previous pipeline, is because if developers are making if we are inserting static code analysis in the feature push, the code analysis should not take significantly longer than it takes to compile that code. In the world of microservices, in the world of Lambda functions, the pace of change is very, very high. The amount of code that is being written is much smaller. Microservices, 100 to 200,000 lines of code. Lambda functions far smaller than that. And if for even these small applications, if the code analysis is taking 10, 20 minutes, that just adds up. Concurrent scanning. Well, even in a small development team of 100 developers, if each developer's feature push is being analyzed, it's obvious that we are now going to have scenarios where at any given time, multiple feature pushes need to get analyzed. And if you are using an on-prem static code analysis solution, this really starts to cost a lot of money and resources. Static code analysis is a very compute and memory intensive application. And in order to analyze multiple feature pushes simultaneously, you might have to buy multiple boxes. If you're trying not to impact developer productivity, you might have to spend more money on licenses. And you are anyways starting to rapidly adopt the cloud for all its advantages. It's time that we started thinking about the same for static code analysis, because it has significant advantages of where you get to outsource the day-to-day management, the upgrade of software, the new rules that are coming up every so often to make application security more important. And finally, of course, to be able to do things like concurrent scans by using highly elastic pipelines in environments like AWS and Azure DevOps and Google Cloud. Accurate. Well, we in the last 10 years or so as an industry have started to use a lot of open source libraries and a lot of frameworks. Now, if you go back to static code analysis tools that were started, those companies were started roughly about 15, 20 years ago, when there was barely any usage of libraries and frameworks. These architectures are not built to analyze modern applications, and so they take shortcuts, causing false positives, causing false negatives. This is what significantly impacts developer productivity. So if we are going to do this right, we need modern tools that are purpose-built to analyze modern applications that are far more accurate than legacy static code analysis solutions. Purpose-built for developers. In our own analysis, we find that about 60% of the application security work is done by developers. And that is obvious, because while the application security team runs the tool, finds the vulnerability, it is still the developers for the most part who have to find out whether it's a false positive or not, and to actually go fix the code. And so developers are the ones who are the primary customers of the CI pipeline. And so if we are to seamlessly wanting to insert the code analysis in this developer workflow, we need to build tools. We need to build experiences that are purpose-built for developers. And we'll look at that a little bit later on in this slide deck. Policy-driven. No two organizations are the same, and therefore no two applications across two organizations are the same. You might have certain requirements for the encryption levels or the libraries that you're using for implementing two-factor authentication. And so is there a way to teach the tool your environmental specific requirements so that the accuracy is further tuned to your environment? Now, while in the previous CI/CD chart, we saw how can we insert security to the left, is there a way that we can move security even further left by actually making developers better developers who write code more securely? Let's explore that in a later slide in this deck. Modern use cases. If you're starting to use cloud environments, like we discussed, secrets, credentials, leaking data to S3 buckets that are exposed to the outside world, these become very, very critical elements that in addition to looking for SQL injection and cross-site scripting, we need to be looking for them accurately. Now, as we think about these requirements, the obvious question that comes up is, well, is there such a technology that allows us to deliver on all of the requirements that we just discussed? Well, and guess what? We have developed such a technology. We call it the code property graph. Now, what is unique about the code property graph is that it takes multiple compiler representations of a source code and stitches them together into one hyperdense graph, and uses modern graph databases so that the relationships between all the nodes and edges is maintained. How is this different from sort of legacy approaches? Well, legacy approaches for static code analysis do not take multiple compiler representations such as the ones highlighted here. Number two, even when they take some compiler representations, each of them is persisted as separate graph. And so finding results across these graphs becomes hard. It takes more time. It causes more errors. And finally, many times this data is stored in a flat file or a relational database, which one has to make compromises in order to store a graph-like format into a relational database. And those compromises start to impact, again, both performance as well as accuracy. Above all, the thing that is most important for web applications is the data flow. To understand how data flows from one part of the application to another, because after all, an attacker-controlled interface where someone is submitting a username, if not sanitized one, to see whether that eventually makes it into a SQL query is how we would try and detect whether it's a SQL injection attack. Now, data flow crackers become very hard to create for modern, highly dynamic programming languages like JavaScript. And so when you look for a tool, look for such details. Here is an example of why context of open source libraries in this particular case is important. It's not just important to look for to find out whether you're using a vulnerable library or not and whether you should upgrade. But even when you are not using a vulnerable library, it is important to understand how the data flows through your custom code, through the library, to perhaps a framework, and finally to a sensitive sink. Because only when we completely understand the entire flow from the source to the sink can we accurately predict whether this is a vulnerable flow or not. And legacy tools, as you can see now, if they do not understand the open source library really well, typical implementations will stop the analysis when the data is entering a library, thereby causing both false positives or false negatives depending upon the application. And so in a code property graph-like technology where we are taking multiple compiler representations of the entire application, which includes custom code, libraries, frameworks, and APIs, because APIs increasingly are a very integral part of our application so that it can talk to various other third-party services that the application might be using, such as Twilio. And so understanding both the context of the library in which it is being, in the context of how this application is using this library, what are important data elements that need to be protected, and how they flow through the entire application to the sink becomes absolutely critical. What are some of the other advantages of code property graphs? We dug too deep in the last two slides looking at code snippets. My head was already starting to hurt. If we step back and if we ask ourselves, what are some of the other advantages of this code property graph technology? Number one, it's super fast. So it can analyze about 1 million lines of code in under 15 minutes. It can analyze about 250,000 lines of code, a bigger microservice, if you will, in about 28 seconds on average. It is highly accurate. Based on the OWASP benchmark, the accuracy of code property graph-centric static code analysis is about 3 times higher than anyone else in the industry. And this goes back to 2 key reasons. One, because code property graph takes information about the application that other approaches don't, it sees more. And because it sees more, it is able to analyze more thoroughly. Number two, because it does complete data flow from every source to every sink, it is much more accurate, thereby minimizing false positives and false negatives. In the OWASP benchmark, CPG-based technology not only was the most accurate, but also was the only technology to find 100% of the vulnerabilities, i.e. 0% false negatives. Business logic flaws. Clearly, if first step is to implement a next generation static analysis tool into your CI pipeline, into the pull request, so that as an organization, you get better at fixing the number of vulnerabilities you are finding. But once you've gone through that journey, you will want to ask yourself, how do I get even better? And this is where the notion of business logic comes in, where you get to tell the tool about environmental specific elements that the tool should take into account when analyzing your code. And we will look at a few examples later on. I've talked about unlimited concurrent scans. If implemented in a high elastic cloud environment, code property graph can be created and analyzed for every feature push. It's not one pipeline architecture, or it doesn't have to be, a one pipeline architecture where multiple feature pushes are waiting for the ones prior to them to be completed, because the goal has to be to provide developers with immediate feedback of the vulnerabilities at roughly the same time frame that they get information on the bugs caused by their change. And so here is where we get to double click and take a look at what this experience might look like. So here is a GitHub screenshot. There's a developer here by the name, in this example, called Arun Machari, and he has this application called Hello Shift Left. It's a Java application, and he is doing a pull request. He's made a change, and he's submitting this change to be accepted. As soon as that happens, this pipeline has been configured to run Circle to compile. And notice the build was successful. While it is hazy, you can see that the entire process for this application took about 3 minutes, which included the build, but also in parallel, notice now that the code analysis was kicked off in parallel. And so in the same interface where the developer is used to seeing whether his change was successfully compiled or not, he gets immediate feedback on whether the code analysis was successful or not. And this is not to say that the code analysis failed, meaning it wasn't able to analyze, but this is to say that the requirements set by the application security team for this application caused the code analysis to fail and not allow this pull request to be merged. Now, of course, as a developer, the obvious next question is, well, why did this pull request get rejected? Well, the information, again, is in the same interface. The idea is not to ask developers to go to a different tool, because that impacts their productivity. We cannot expect them to be using 6 different tools to make sure that their application is secure, developed securely. So in the same interface, the developer gets the URL for the vulnerabilities caused by his change. And of course, as the next step, he clicks on it and gets to an interface which tells him the vulnerabilities, 3 new vulnerabilities caused by this new pull request. You can click on it and get details of the exactly 3 vulnerabilities, with plenty of other supporting evidence, such as the entire data flow, which illustrates why this vulnerability is called out, and also help in how to fix this vulnerability so that the mean time to repair can be significantly reduced. Now, having seen how can we insert code analysis into a CI, a modern CI/CD pipeline, how can we insert code analysis into pull requests, let's push this boundary a bit further. Let's ask ourselves, is there a way we can further automate this? As we discussed earlier, developers cannot be security experts. It's application security that has the broader purview across the organization. So in a good implementation of static code analysis, the application security should be able to write a simple YAML file like this. It says, well, this is a build rule. It's called fail on critical vulnerabilities. And it is essentially saying that if I ever see a SQL injection or a sensitive data leak, which has a high severity impact, if this vulnerability or these kinds of vulnerabilities are ever seen in a pull request or in a feature push, fail that build. Now, with a simple YAML file where such build rules can be created, one can easily insert them into the CI pipeline so that the application security requirements are translated as code, like we discussed earlier, and inserted into the CI pipeline. Most organizations have a ratio of about 100, 200, maybe sometimes even 500 developers to one application security person. So to expect one application security person to be able to do his or her current job with legacy static code analysis tools leads to disaster, leads to application security failure. But now, with an approach like this, we have allowed the application security team to communicate their requirements to all the developers within a workflow that developers are very familiar with. Now, we talked about how each application, each environment is unique, and developers are the ones who know these environments the best. And so can we, in parallel, provide developers the ability to write yet another YAML file where they can specify what are the characteristics which are unique to their environment. So here they are saying that the PII data is defined as variable first name, last name, maiden name, or the PII is also defined as email, etc., etc. And now that we have informed the tool that this is what PII in my world looks like, the tool can now start looking for these variable names and to see whether they are being sent to a sink, sent to a destination without any authentication, without any encryption or obfuscation. Imagine in highly regulated industries where we have a good sense of this data and what these data variables might be. Now we can automate with every feature push that the change that was just made is not going to cause me to leak highly sensitive data. Is not going to cause me to write highly sensitive data to the wrong place. Hopefully you're starting to get a sense of how these simple steps, but very powerful steps, leveraging a unique technology like code property graph can truly help us start to automate application security in a modern pipeline. Let's take a step back and let's ask ourselves, how does this new approach compare with the older approach? Well, we've often heard that with using legacy code analysis tools, some customers get results within 2-3 days. Clearly, that is way too long. With this new approach, we need to start doing this in minutes to seconds. Based on some of the things that we talked about of what happens when we run a scan much later in the pipeline, is we start to impact developer productivity. We start impact, because we are causing developers to switch context, we are starting to impact how long it takes them to understand, identify the root cause of the vulnerability to actually fix it. Tuning policies with these legacy technologies can be very hard. You might need to use some proprietary language that a vendor has created to write specific sorts of rules. And sooner or later, these rules, once initially organizations get enamored and they write a few rules, but then it becomes impossible to maintain these rules over time. And that's one of the things that I forgot to mention in the previous slide, because these are YAML files, and we can start using the same Git-based peer review mechanism to get these changes approved. And what's more, we can even use Git to keep a version control on these changes so that there is no new system that the developers or the application security teams are having to remember. Now it'll be easy for us to go back to find out, hey, why did some who 9 months ago made this YAML rule to fail such a build, and why was this rule created to begin with? What's the logic behind it? So that 9 months later, as we're looking at this YAML file, revisiting whether this is good logic in today's context or not, we have those answers at our fingertips. Resolution time, goes from days to weeks to hours or minutes. I'll give you a very powerful example. There is a very widely read report that gets published in the industry every year, which talks about how 70% of the vulnerabilities found are not fixed. Period. Not fixed. And when you start to implement the CPG-based approach very seamlessly into the CI/CD pipeline, you flip the problem on its head. The data that we are seeing is that about 70% of the new vulnerabilities found are fixed within the first 3 weeks. Now that is a that is a metric for an application security team to be proud of. When we compare and we take all of the elements of the previous slide and try to do a TCO, a total cost of ownership analysis, one typically finds that a highly fast-paced, highly accurate SaaS tool inserted into the CI pipeline costs about 1/6 of a legacy static analysis implementation. Now, some of you in the audience might be asking, well, static code analysis is just one way to find vulnerabilities. What about IAST, or what about, making better use of architectural requirements to insert them into static code analysis or some tool? And finally, how to get better at protecting applications in production. What I'm trying to say in this slide is the biggest impact that any application security team sees is by first implementing a static application security tool in a modern CI pipeline, as we discussed in the first 30 minutes of this discussion. And once you've done that, now it's a good time to start thinking about how to evolve the application security further, but perhaps thinking about technologies like IAST, interactive application security testing, that are a good complement to static code analysis. Because the fundamental problem that static code analysis suffers from, one of its key weaknesses, is that it cannot tell you whether the vulnerability that it found is exercisable, whether the vulnerability it found on line 100 ever runs in production. That is where IAST or DAST, which is sort of the legacy of IAST, comes into play. But here also we could do better, is if this is the biggest deficiency of static code analysis, why shouldn't we take the results of static code analysis so that we can instrument the application based on this knowledge of the attack surface of the application, run our own QA tests that we run, ideally production traffic that we run in QA. And now we can see whether that vulnerability on line 100 actually is exercisable or not. And what's more, we can also see whether it sees 100 calls per minute or 5 calls per minute. Now, with that data, we can start to prioritize vulnerability not just based on OWASP severity, which remains the same for every company around the world, but based on the unique characteristics of our environment. Business logic or architectural requirements or even pen testing, penetration testing results can be used to highlight policy changes that we should make in order in order for static code analysis to detect the same vulnerabilities that you would have otherwise detected by using either manual code reviews or by doing pen testing. Now, that's not always the case. Pen testing tests the entire stack, not just the application. And the field of view for static code analysis is just your application. So there are reasons for also doing penetration testing that go above and beyond just finding vulnerabilities in an application. And finally, operate, which is when you're running the application in production, how do we prevent it? Historically, we've used approaches which essentially write signatures for threats, and because threat landscape continuously evolves, the vendors just continue to write more and more and more signatures or rules or algorithms, whatever they are called in the vendor's language. But this is also where we believe as an industry we can do better by leveraging, again, the knowledge provided by static code analysis about the attack surface of an application. If we know that this particular application only has one SQL injection vulnerability on line 100, it becomes very clear what do we need to do. Well, we need to protect that line 100 from SQL injection, not cross-site scripting, not directory traversal, nothing else but SQL injection, because that's the vulnerability. On the other hand, if there is an application which we know does not have any SQL injection vulnerability, why spend resources running a production tool which will create an alert or hundreds of alerts because it sees a dirty pattern which it thinks might cause a SQL injection vulnerability, and overload our SOC? Because every alert that gets created, well, if you're not looking at it, then you're just wasting everyone's time. Now, all of this cannot be done by developers, and neither can all of this be done by application security people. That's the beauty we find with this CI/CD pipeline. First and foremost, it shows up in this collaborative environment that DevOps creates. But this is our perspective, which is that at each stage of this development pipeline, the function responsible for that step can enhance application security. During planning, when we are writing the architecture of the application, where we are writing the requirements of that application, as we discussed earlier, can we take some of that knowledge and write simple YAML rules that allow the code analysis tool to leverage it as a policy? Static code analysis clearly needs to be run during software development, during coding, as we discussed by discussing how do we insert SAST, next generation SAST, into the CI pipeline. During build, which is an integral part of coding. Test, we talked about how we can start to leverage the knowledge of the attack surface to specifically understand which vulnerabilities are actually going to be exercised in production so that we have further information on how to prioritize fixing of those vulnerabilities. Release is all about deciding whether this application is ready to go in production or not. And by, again, automating the application security requirements and rules that are fed into the CI pipeline, we can start to see how we can achieve this automation. And finally, in deploy, operate, and monitor, we are running the application in production by instrumenting an agent that has the knowledge of the attack surface. So we are doing a far better and accurate job of protecting the application in production. With that, I thank you very much for your time. Hopefully this was a productive session for you. The three key takeaways that I would summarize towards the end is CI/CD pipeline and DevOps is here. Application security is being left behind, number one. Number two, application security is going to be successful by inserting next generation static analysis, not legacy static analysis tools, seamlessly into the CI/CD pipeline. And third, static code analysis tools have to appeal to developers, have to seamlessly fit into the developer workflow, because 60% of the work for AppSec is done by developers. If you hold three of those things as key requirements as you think about how to design your application security requirements for the tool of your choice, you will do well. Thank you very much for your time.